Hello, greetings to everyone and welcome to this video lecture on cosmology. In the previous lectures, we saw Newtonian and Galilean mechanistic conception of the universe and how it is in contrast to Aristotelian view and to the new quantum mechanistic conception of the universe. In today's lecture, we make a contrasting study by Einstein's theory of relativity. In this, we see how Newton's fundamental categories of space, time, matter and motion are radically reinterpreted and applied to the universe as a whole. This new interpretation takes us to a completely new cosmology, taking us to a new view of experiencing the physical universe. Now, what is theory of relativity? Theory of relativity is one of the greatest scientific achievements of man. Its author is, we know, the great scientist Albert Einstein. This theory consists of two parts. One, the special theory of relativity presented in 1905, and the second, the general theory of relativity proclaimed in 1916. The special theory deals only with objects or systems which are either moving at constant velocity with respect to one another or which are not moving at all. That is, it concerns about the unaccelerated systems in the universe. The general theory treats of objects or systems which are speeding or slowing down with respect to one another. That is concerned about accelerated systems. Now, it will be easier to understand the theory of relativity by using an example. Now, let us think about, we have two flashes of lightning exactly at the same time in points A and at points B. A and B at two different points are the points of two flashes of lightning. Let us take A and B as points of beginning or end of a line or a road. Now there is an observer, observer 1, who exactly is on the middle at the same distance from point A and from point B. The observer at the middle is motionless and it perceives the two flashes of lightning simultaneously from point A at one end and point B at the other. Now, there is another observer, observer 2, who is closer to point B and moves towards it, perceives the same flash of lightning differently than the observer at the middle, that he perceives the flash of B first and flash A later on. In consequence, it is deduced that simultaneousness is nothing absolute but something relative. It depends on the physico-mathematical system which the observer used to observe. Thus, in fact, it is true what both observer, the first observer who is at the middle, exactly at the middle between A and B, and the second observer who is more closer to B than A, the lightning shine at the same time at a different time really. Thus, the first assertion is true according to the system of the first observer, and the second assertion is true according to the system of the second observer. Thus, each system coordinate or the coordinate system has its own time. Therefore, it will be insufficient to mention time if you do not specify according to which system you mention time. It is clear then that time cannot be considered like something homogeneous and independent from space as classical physics used to believe. Thus, it is the explanation accepted in the special theory of relativity. It is based on two postulates. Now, what is the special theory of relativity? There are two postulates assumed in the understanding of the special theory of relativity. First is that all inertial frames are to be regarded as equal and that there exists no absolute frame of reference whatsoever. To be more precise, the laws of physics are equivalent in all inertial frames of reference, which are moving uniformly with respect to each other or are at rest. Hence, there is no any privileged frame of reference like absolute space, which was thought to be the absolute background of all motions in the universe. The second postulate affirms the constancy of the velocity of light. It states that the velocity of light is a universal constant, that it is the same in all directions and the same in every inertial reference frame independent of the frame's motion. To be more precise, the speed of light remains constant at 186,000 miles per second, that is 300,000 kilometers per second, irrespective of the motion of the source of light. That is, no matter how fast the source of light or observer moves, the speed of light is constant. The velocity of light is constant, that is 186,000 miles per second, no change. The velocity of light, in fact, is the only constant of absolute in the theory of relativity. Now, based on these postulates, the special theory of relativity describes how different dimensions of physical reality, that is length, time and mass, appear to be varying. Depending upon the point of view of different observers, this length, time and mass appear to be varying. How is it that? It tells us that appearances of these dimensions are dependent upon the state of motion of the observers. That is, they depend upon their state of motion relative to each other. Thus, the theory of relativity states that it is not a theory that everything is relative, but rather it is so the way the world exists and appears to human perception and comprehension are relative. For example, the theory of relativity tells us that a moving object measures shorter as its velocity increases, that moving clocks runs more slowly as their velocity increases, and that the mass of a moving object increases as its velocity increases. Now let us see what is the relativity of motion. The theory of relativity has its beginning in the question whether motion is relative or absolute. The following consideration shows that motion is not of absolute but relative. Suppose you are alone moving at high speed out in space, far away from all the stars and planets. Then you will never know whether you are moving or not. For in order to understand whether you are moving or at rest, you have to refer to some body or some other material in reference. Movement is always in relation to some body. For example, when a train moves, it moves in relation to the earth, which appears to be not moving. The earth travels in its orbit around the sun. The sun and the solar system are orbiting around our galaxy, the Milky Way, and our galaxy is moving relative to the other galaxies and so on. Here we have a number of relative motions relative to some particular frame of reference: the earth, the sun, the Milky Way and other galaxies. That is to say, the train appears to be moving relative to the earth, and earth appears to be moving relative to the sun and the other stars and the Milky Way, and the Milky Way is Milky Way appears to be moving or in motion in reference to other galaxies. Observing these movements, no one can say what is moving and what is stationary. We can only say that all the heavenly bodies are moving relative to one another. If there is a motion, that is in motion relative to some other body. There is no fixed motionless body or frame of reference in the universe. Hence, there is no absolute motion in relation to something motionless body. But until the advent of the theory of relativity, the scientists thought that there is something absolute called ether, an invisible, tasteless, odorless substance permeating the whole universe, one motionless object at absolute rest, something as motionless. And motion of a body with respect to the ether was thought to be absolute motion, and a body at rest was considered to be in absolute rest with respect to ether, that is absolute. Ether alone was considered as remaining motionless in the background of all the moving heavenly bodies. Moreover, it was proposed to be the medium for the propagation of light, since as we know that sound waves travel through some medium such as air, it was thought that light wave also has a medium to travel. Thus, ether was considered to be the medium for the light waves to travel. It was suggested that light waves travel in ether, which permeates the entire universe and is absolutely motionless. Light travels at a velocity of 186,000 miles per second through ether. That was the conception till the theory of relativity. Albert Michelson and Edward Morley conducted an experiment to determine whether ether exists or not. They sent out light signals in two directions at right angles at each other. Each was reflected from a mirror and came back to the place from which both had been sent out. Now, if there were either one of the two light signals, which consists of waves in the trailer, would travel from the mirror and back at a slower rate than the other, but not even the slightest difference of speed light was observed. Both light signals came back at the same velocity. That is, the Michelson-Morley experiment failed to prove the existence of the ether as a medium of light. Moreover, it proves the constancy of the velocity of light. Ether was thought to be the frame of reference in relation to which absolute motion takes place. If there is no ether, then there is no absolute motion either. Thus, the first postulate of the special theory of relativity that all motion is relative, and that is impossible to detect either. Michelson-Morley experiment at the same time was a proof for the constancy of the velocity of light. The experiment showed that unlike and unaffected by the relativity of motions at a different speed on Earth, the velocity of light is same in all directions. We can clarify this peculiar behavior of light by the following examples. Take the example of a boy throwing a ball at 15 miles an hour while at rest. This means that the ball travels at the rate of 15 miles an hour relative to him who is at rest. Now suppose the boy is traveling on a truck at 5 miles an hour, and as the truck moves towards an overbridge, he throws the ball towards the bridge at 15 miles an hour. The ball will hit the bridge at a 20 miles an hour impact. Suppose the boy is throwing the ball as the truck is moving away from the overbridge. The ball will hit the bridge with only 10 miles an hour impact. In a similar way, let us now suppose we are standing still observing a star from the earth. The light from the star will reach us at 186,000 miles per second. But supposing the star and the earth are approaching to each other with a relative velocity of 100,000 miles per second, we would expect that this velocity is to be added to the speed of light in the same way as the velocity of moving truck is added to that of the thrown ball. That the light should produce a 286,000 miles per second impact on the observer's eye. Now, if the star and the earth are receding from each other with a relative velocity of 100,000 miles per second, we would expect that the light should produce an 86,000 miles per second impact on the observer's eyes. But in both cases, light produces a 186,000 miles per second impact on the observer's eye, no change. Thus, the speed of the light remains constant irrespective of motion of the source of light. That is to say, we can neither add nor subtract to the speed of light, and that is the second postulate of the special theory of relativity, that the velocity of light remains constant no matter how fast the observer or the light source move. This means that a light wave leaving a star will have a velocity of 186,000 miles per second relative to an observer, regardless of whether he and the star are approaching or separating at a relative velocity of 185,999 miles per second or 1 miles per second, no matter. Now, this velocity of light, the constancy of the velocity of light has some certain consequences, very interesting consequences. The constancy of speed of light has some important consequences for the properties of material bodies in our perception and understanding of them. The properties such as length, time, and mass are relative to the state of motion of the material bodies. Hence, there is no absolute length, time, nor mass. Length contracts, time dilates, mass increases with motion. Thus, at first, the constancy of the velocity of light implies the relativity of length. Thus, a moving object appears to contract and become shorter as its velocity increases. Suppose A and B are in two rockets, each 20 feet long when they are at rest with respect to each other. Now, if they are separating at a relative velocity of 93,000 miles per second, and if A measures the length of B's rocket, it would appear to be only 17 feet. If they are separating at a relative velocity of 161,000 miles per second, the length of B's rocket would appear to be only 10.1 feet. But if A measures the length of its own rocket, and it will find it to be 20 feet long, no change. But if B measures the length of A's rocket, it will find it to be 17 feet long at 93,000 miles and 10 feet at 161,000 miles per second. If B measures its own rocket, it will find it to be 20 feet long. Therefore, the effect of the contraction of length can be stated as follows. That is, whenever one observer is moving with respect to another, whether approaching or separating, it appears to both observers that everything about the other has shrunk in the direction of motion. At the same time, neither observer notices any effect in his own system. Such contractions of length takes place even at ordinary velocities. The fact is that since these are much lower than the velocity of light, we do not notice it. For example, an aeroplane flying at 750 miles per hour contracts 1 millionth of an inch. Hence, we must give up the classical notion of an absolute length which is the same value everywhere. Now, another consequence is the time dilation. As a result of motion, time appears to be slowing down, and this is called time dilation. That is to say, a moving clock runs more slowly than a clock at rest and continues to slow down as its velocity increases. These effects appears only to a stationary observer, one who is at rest, relative to the moving clock, and do not appear to an observer who is traveling along with the clock and rod. From the point of view of the person who is moving, the situation is reversed. He is at rest and the stationary observer is moving. The time dilation effect states that if two observers are moving at a constant velocity relative to each other, it appears to each other that the other's time processes are slowed down. Take for example, the clock of A and B read the same time, 10 o'clock, when they are on Earth. Now suppose they are separated at a relative velocity of 93,000 miles per second. If A's clock reads 11 o'clock, A finds that B's clock reads only 10:54, that is 6 minutes slower. If their relative velocity is 161,000 miles, A will find B's clock to be at 10:30, while itself reads 11 o'clock. Now, if B measures A's clock, it also get the same results at the respective velocities. But if each one measures its own clock, it will not find any difference. The time dilation effect can be therefore stated as follows. If two observers are moving at a constant velocity relative to each other, it appears to each that the other's time processes are slowed down. Hence, we must give up the classical notion of an absolute time order which is the same everywhere. That two events simultaneous here are simultaneous all over the universe is to be given up. The verification of time dilation comes from high energy physics. When elementary particles called muons are created in accelerators, they live a very short time. But muons created by cosmic radiation live 7 times longer than those muons created in the laboratory. Because muons produced by cosmic radiation travel much faster than almost 99% of the speed of light. They do not live longer than usual from their point of view, but from our point of view, they live 7 times longer than they would at lower velocities. This is true not only of muons, but almost all subatomic particles. Another consequence of the constancy of the velocity of light is the increase of mass with velocity. According to classical physics, mass is the constant property of a body totally independent of its motion. Hence, it will have the same value for all observers, whatever be their rate of motion. But when we look at it in a special theory of relativity, the special theory shows that mass of a moving object increases as the velocity of the object increases. Hence, Mass is not an invariant property of a body but increases with its velocity. This increase of mass can be explained as follows. A moving object has kinetic energy or energy of motion. When an object is in motion, some of its kinetic energy is converted into mass. An object moving at a very high velocity has much additional kinetic energy. This additional energy makes it behave exactly as if it had more mass. Suppose A and B each have mass of 100 kg on Earth when they are at rest with respect to each other. Now, if they are separating or approaching each other at a relative velocity of 93,000 miles per second, A would find B to have a mass 120 kg. At 161,000 miles speed per second, and B's mass as measured by A would be 200 kg. And if B measures A's mass, it too will find similar increase of mass with the increase of speed. But each will find its own mass to be 100 kg only, regardless of how it is moving relative to anyone else. The mass increase law states that when an object is moving with respect to an observer, the mass of the object increases depending on the relative velocity of object and observer. Both would not observe any change in their own respective mass. Thus, when subatomic particles travel at velocities approaching the speed of light, their high kinetic energy makes them behave as though they have more mass than they have at lower velocities. Now, based on this, we have a very curious result of equivalence of mass and energy. According to the special theory of relativity, mass is a form of energy and energy has mass. Mass and energy are the same. The formula which expresses the relationship between mass and energy is a very famous formula made by Albert Einstein. E is equal to mc square, where E is energy in ergs, and m the mass in grams, and c the velocity of light, that is 186,000 miles per second. The energy contained in a piece of matter is equal to the mass of the matter multiplied by the speed of light squared. This means that even the tiniest particle of matter has within it a tremendous amount of concentrated energy. So, in the process of breaking up atomic nucleus into smaller pieces, the mass of an atom is converted into energy. The total mass of separate pieces is less than the original mass. The lost mass is converted into energy. Thus, when a 92 uranium atom is split, the result is 56 bariton and 36 krypton. The rest of the mass is converted into energy. The amount of energy released follows the formula E is equal to mc square. This process of splitting a heavy nucleus into two or more fragments, thereby releasing energy, is called fission. And this is the process taking place in atom bombs and nuclear reactors. The opposite of fission is fusion, which consists in fusing lighter atoms such as hydrogen to form heavier ones such as helium. Fusion takes place in hydrogen bombs and in the stars. Mass of a hydrogen atom is 1.00797. Mass of 4 hydrogen atoms is 4.03188. 4 hydrogen atoms are fused to form one helium atom. but the mass of one helium atom is equal to 4.0026. The lowest mass, that is 0.73% of the whole, is converted into energy. In the sun, 680 million tons of hydrogen is converted into helium at every second. Thus, 4.6 million tons of hydrogen is converted into energy. This is the equivalence of mass with energy. And these are the curious consequences that we find in our observation of the physical universe with the special theory of relativity, which gives a view of the universe much different from that of the classical physics. And it is much more curious and interesting is our experience of the universe with general theory of relativity, which we will be dealing with in the next lecture. Thank you.